Okay, welcome to Unit 4. We start off with organic chemistry, and that's the chemistry of carbon compounds. We're going to start off looking at hydrocarbons in the first lesson, isomers, naming, structures and so on. And then in the second lesson it will be all about the functional groups. Use the study design as a bit of a checklist with these topics. Just make sure you've got all the different bits. Now, carbon is special. Just about everything to do with life is based on carbon, and it's the properties of carbon that enable this wonderful diversity of life to exist. So it forms 4 bonds. That means it can bond to 4 different atoms. You get a huge diversity of different atoms joined together in carbon-based molecules. So nitrogen and phosphorus can only form 3, oxygen and sulfur can only form 2, but carbon and silicon can form 4. There's an issue with silicon that we see later on. Its bonds aren't strong enough. Now, just recognise that the shapes of molecules based on carbons with 4 bonds are tetrahedral. Now, we might draw them simplistically like this, basically for ease of understanding, but in reality, they're 3-dimensional tetrahedral structures that do take a little bit of getting your head around. And the actual shape of so many organic molecules is critical to their function, so it's something that we can't really ignore. Carbon compounds form isomers. That means you can get the same combination of atoms connected together completely differently. So C3H7O2N can be a whole range of different molecules. Only one of these is useful in the body, and that's L-alanine. Carbon-carbon bonds can be single, double or triple. If they're all single bonds, we call it a saturated molecule. If there are carbon-carbon double or even occasionally triple bonds, we call it an unsaturated molecule. Carbon-to-carbon bonds are strong. So the molecules based on strings of carbon atoms are strong molecules. So silicon can also form 4 bonds, but its bond energy is much, much less than a carbon-carbon bond. So its molecules based on that are going to be much less stable. Stable molecules, difficult to break down, more useful in all circumstances. Okay. Do this question, submit your answer, basically summarising what we've just been over. And then let's have a look at a little bit of, just to get our heads around the different ways of representing chemical formulas. So a structural formula contains a lot of detail about how the bonds are join the atoms together. So propane, got a carbon-to-carbon double bond and then another single bond and all the hydrogens are attached. Structural formula shows the actual bonds present in the molecule. Now we can simplify that down to a semi-structural formula, basically a line of text, which has all that information in a distilled form. That's formally the semi-structural formula, correct semi-structural formula. I don't mind putting the double bonds in like that just to make it obvious where the double bonds are without having to count the hydrogens and think about it. That's a semi-structural formula. Now we can reduce it to a molecular formula, which is just the total number of each of the atoms in the molecule. So propene has 3 carbons and 6 hydrogens. And of course we remember from last year, empirical formulas, which is the simplest ratio of atoms in the compound. So propene has got twice as many hydrogens as carbons, so we can reduce it to a empirical formula of CH2. Skeletal structures are really good ways of conveying information about organic molecules, which leave out the hydrogens altogether, pretty much, and actually just show the bonds between carbons. You don't even write in the C's. So for propene, skeletal formula is like that. So if you need to draw a skeletal formula, what do? You know you've got 3 carbons in a row. So you are going to have, so 1 carbon, you go to a 2nd carbon drawing a line, and then the 3rd carbon, just do it at an angle like so. Now you know between 2 of the carbons there's going to be a double bond, so you put that double bond in. That becomes the skeletal formula. For the next one, butanoic acid. Now what have we got this time? So we start at the end. We've got a carbon, then we go to the next carbon, and then the 3rd carbon, and then the 4th carbon. Now off the 4th carbon we've got 2 oxygens, one with a double bond, one is an OH. So we'll put them in. So double bond, I'm going to do it at right angles. There's no absolutely essentially correct way of doing it. And then the next bond goes to an oxygen and then a hydrogen. So that's the way I would do that, and that's the way it was over there as well. Then we have something like linolenic acid. Now, I think it's big organic molecules like this which really show the power of skeletal formulas. Just so much easier. If you look at that, you see the essence of the structure so much more quickly than wading through all the hydrogens and carbons on that. 3 double bonds, all in a particular cis arrangement, and it's a fatty acid. It's got a carboxyl group. See that instantly just by looking at it. And we draw it the same way. We would just start here, do zigzag, 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 zigzag all the way down, chuck in the double bonds where appropriate, and put the carboxyl group on the end. Isomers. Different ways of arranging the same number and type of atoms. Now, unique properties. Why they're important. In particular, biologically, where shape is so important, all sorts of isomerism is critical. So structural isomers are where you connect the atoms in a different order. So methylpropane versus N-butane. Just note, whenever we've got a straight chain molecule, straight chain isomer of a molecule, we call the straight chain version N. And just to distinguish the fact, we're actually talking about 4 carbons in a row when we talk about butane. We're talking about that particular isomer. We're definitely not referring to methylpropane. So the straight chain isomer is always called N-butane. So same molecular formula, different structural formula. Stereoisomers are where you get different arrangements in space. So, 3-dimensionally, on paper these look pretty similar, but 3-dimensionally they are unique, and different shapes makes different both physical and certainly biological properties. So first of all, structural isomers. Atoms are connected in a different order. Same molecular formula, but different structural formula. So let's draw and name the structural isomers of butene. So what's butene? I'm sure you all remember but is 4 carbons. Ene means it has a carbon-to-carbon double bond. So C4H8. So we've got to link together 4 carbons, and the way we link together 4 carbons has to include a double bond in it. Now the trick is, start off with the isomers of the parent alkane. So start off with butane. When you get all the different isomers of butane, you go through each one in turn and find the different places to put a double bond. So we start off, we can have 4 carbons in a row. It's going to be based on N-butane, and we've got the ones based on methyl propane. There are no other isomers of butane. Now we're going to take each one of those in turn, and we're going to put double bonds in all the different places. So first of all, double bond can go there. Where else can it go? It can go in the middle. Can it go between those 2 carbons? No, because that would be exactly the same as this one. So they're the 2 options for a double bond in N-propane. What about in N-butane? What about in methyl propane? Well, we can put a double bond there. Is there anywhere else we can put the double bond? No, because in each case it's going to be between the end carbon and one of the middle carbons. So there's only 3 isomers of butene. Of course, at that point we would put in all the hydrogens. Make sure you can count properly. It's really common for people to just miss one hydrogen here or there. That carbon's already got 4 bonds. And we should really hope that we've got 8 hydrogens on each one of those molecules. No, we don't. We need another one there. And that looks all good. So now we're going to name them. So we've got 4 carbons in a row. But, got a double bond starting at carbon number 1. But 1 ene. Here the double bond starts at carbon number 2. But 2 ene. And then methyl propene. You can say 1 methyl 2 methyl 1 propene if you like, but really that's the only arrangement that works. Now for a slightly neater version of all that. And there we have the answers. Chain and positional isomers are different types of structural isomers. So chain isomers are different arrangements of carbon in the chain. So N-butane, methyl propane are chain isomers, whereas positional isomers are different locations of the functional group. So if the functional group is a double bond, 1 butene, 2 butane, have the double bond in different places, therefore they are positional isomers. And molecules, of course, can be both, as in the case of those 2. Have a go at those questions, submit them on Google Classroom, pause the video now and come back when you're ready. Okay, now we look at optical isomers. and geometric isomers, stereoisomers in general. So what we have is atoms connected in the same order but different arrangements in space. So first of all, optical isomers. They're basically mirror image molecules. Optical, because one way of detecting them is the fact that if you shine polarised light through a purified sample, they rotate polarised light in different directions. Geometric isomers are where you've got different arrangements around double bonds, so cis and trans isomers. So first of all, optical isomers. Chiral refers to a type of substance that has optical isomers. So basically, chiral objects are objects that can't be superimposed on each other. So you can't put your two hands in exactly the same way over each other. You can only do it with them facing in opposite directions. Lots of objects in nature are like that, and lots of molecules are like that. Two objects which are mirror images that cannot be superimposed. They are chiral objects. Achiral objects can be superimposed. So the mirror images are identical, they can be superimposed on each other. So these two here, we can rotate that second one around 180 degrees and then they'll be identical. Now, key to identifying chiral molecules is that they've got 4 different groups attached to the carbon. Now, the two enantiomers, the two mirror image versions of a chiral compound, have completely different biological properties. Is that different arrangement of particular atoms in space affects all sorts of things to do with protein functioning, enzyme activity and the like. So they are crucial biologically. As we saw before, there are a whole range of different versions of C3H7NO2, and L-alanine is the only one that our bodies can have any use for. The mirror image version of it, D-alanine, is useless. So we see the chiral carbon in L-alanine. It's got 4 things attached. It's got a carboxyl group, it's got an amino group, it's got a methyl group, and it's got a hydrogen. 4 different things makes it chiral. All amino acids are chiral except for glycine, which is the simplest one, in which the R group is a hydrogen. So some simple examples of chirality. Difference between orange flavour and lemon flavour in large part is this particular carbon here is chiral. So one arrangement in space produces an orange flavour, the other arrangement in space produces a lemon flavour. So identifying chiral molecules. Look for a chiral carbon that is a carbon with 4 different things attached. So we just go along the carbons on the chain. Now, the instant we see a double bond, any carbon with a double bond can't have 4 things attached, so it's not chiral. So those two aren't chiral. If it's got more than one hydrogen, clearly it doesn't have 4 different things attached, so those two can't be chiral. Which leaves us with this little one, which has got a hydrogen, an amino group, and it's got a methyl group on that side, and then it's got a propenyl group on the other side. So that's 2 different hydrocarbony bits, therefore that's 4 different things. And they most definitely are all different for carbon number 2. Second molecule, what have we got? Carbons number 1 and 4 clearly can't be, and the side chain one the same. What about carbons 2 and 3? Well, we see carbon 3, there's 2 methyl groups there, they're the same. So carbon 3 can't be chiral. Carbon 2, what have we got? We've got a hydrogen, hydroxyl, a methyl, and an isopropyl. So that looks good. Carbon number 2 has 4 different things. What about this one? Well, when we eliminate everything with more than one hydrogen, we're just left with carbon number 4 in that case. Now, what are the 2 hydrocarbony bits attached? You've got a propyl that side and a propyl that side. They look pretty similar to me. That means carbon number 4 is, whoops, I should have done that. Carbon number 4 is not chiral. That means this is not a chiral molecule. Need to be a little bit careful with rings. So this one, all of these atoms are going to have 2 hydrogens. If you count up the bonds, each carbon here's got 2 bonds, and that means they've got to have 2 hydrogens. So all those are ruled out. What about this one? Well, it's got a hydroxyl, it's got a hydrogen, and then the chain is symmetrical. So if you go around this way, it's exactly the same as going around this way. So that means it's not chiral. Ring is symmetrical, you're going the same, it's the same both ways you go around. But this one, once we've got a little bit of something different attached to one side of the ring, all of a sudden, going around this way is different to going around that way. If you go around this way, the methyl group is 1 carbon away. If you go around this way, it's what, 5 carbons away. So that is a chiral molecule. And yeah, it's the asymmetrical ring that we look at. Which makes that molecule chiral. And, oh, that's another chiral carbon, of course, because it's got a hydrogen, it's got a methyl group, and 2 different structures depending on which way we go around the ring. How many chiral carbons are there in aspartame? Let us identify them. Now, how on earth do we know what the structure of aspartame is? Well, how about we look in our data book? We get that out of our data book, hopefully. So, what do? Just look at all the carbons. So what's that? That's got a double bond attached. That's got 2 hydrogens. That's got different thing, a hydrogen and a different thing. So that's going to be chiral. Double bond, some carbon. This one here, that's got 4 different things. 1, 2, 3, and a hydrogen. Then double bond. Can't be that. Can't be that. It's got a double bond. So just those 2 ones there. Okay, go away and do those. Pause the video now. Submit your answers on Google Classroom and then resume with the next bit of stuff. Okay, now we look at geometric isomers. Now these are ones with different arrangements around a carbon-carbon double bond. Now our study design asks us simply to name them cis and trans, but the actual correct way these days is to do a slightly more elaborate version, Z and E. So we'll be actually doing both of them because it seems not like the right thing to teach incorrect chemistry. Now, why is this important? Well, once you put a double bond in a molecule, it locks the carbons in one particular arrangement in space. Now, cis and trans isomers, just before we get onto that, occur when both the carbons have got two different things attached. So this carbon has got a methyl group and a hydrogen. This carbon's got a methyl group and a hydrogen. Because each of those two carbons has got two different things on it, we have cis-trans isomerism, geometric isomerism. Now, if you've got a single bond between carbons, the carbons can rotate freely. So the chlorines can point away from each other, they can be on the same side, it just depends on what else is going on. They can freely change between those two arrangements. However, once you get a double bond, they get fixed in place. It takes quite a bit of energy to flip them over. There's no rotation around that double bond, therefore they're two distinct structures. So the chlorines are either going to be on opposite sides, they'll be trans, or they'll be on the same side, they'll be cis. And that's what this tells us. If the major functional group's on the same side, cis. If it's on opposite sides, it is trans. So apply that to these. Are the major hydrocarbony bits on opposite sides, or are they on the same side? Opposite side trans, same side cis. Submit your answers on Google Classroom, then resume. Now, as I was saying, the formally correct way of doing it is as E and Z. Basically, it's very similar just to looking at which way the chain continues. It's looking at the two carbons around the double bond. Look for the group on it which has the highest atomic number, the atom which has the highest atomic number. So on this side, carbon has an atomic number of 6, hydrogen has an atomic number of 1. So carbon has a higher atomic number, it takes priority. This side, bromine has an atomic number of 35. Hydrogen, of course, has an atomic number of 1, so bromine takes priority. So in this case, we look at the carbon and the bromine. They are on opposite sides. Therefore, it is E, 1-bromopropene. If they were on the same side, they would be Z, 1-bromopropene. E for opposite, Z for same. Now in this case, it's easy on this carbon. We've got a hydrogen and a carbon. Carbon's clearly got the higher atomic number. What about this side? Well, first atom is a carbon on both of them. If that's the case, we move down the chain one to a carbon on this one and an oxygen on this one. Therefore, oxygen has an atomic number of 8, carbon has an atomic number of 6. Therefore, the hydroxyl side has precedence. So opposite side is E, therefore it is E, 2-ethyl butene 1-ol. This one, in this case, need to be a little bit careful with this one. Right hand carbon, it's clear, carbon takes priority. Left hand one, first atom is a carbon, so that's the same. Second atom on this one's a carbon, second atom on this one's a fluorine. Fluorine has got a higher atomic number, therefore fluorine takes precedence. Both of the groups are on the same side, therefore it is Z, whatever the rest of the name is. So do those questions and submit them on Google Classroom, and then we'll move on to the next bit. So let's go over the different classes of hydrocarbons. Now, first of all, just a definition. What's a homologous series? It's a group of related organic compounds. Each member has an extra carbon, i.e. each member differs by a CH2 group from the previous member. Same functional group, different length of carbon chain. So, alkenes, first of all, containing a carbon-to-carbon double bond, a single carbon-to-carbon double bond. They're known as unsaturated hydrocarbons. And the big reactivity, big thing that alkenes do, double bonds do, is they react in addition reactions. And the classic test is to react them whether with hydrogen or bromine. So you get your sample of unsaturated hydrocarbon, you add as much hydrogen or bromine as is needed, and when all the double bonds are reacted, you've saturated the molecule with hydrogens or bromines. That's when it becomes saturated. Alkanes have all carbon-carbon single bonds, and they don't react with hydrogen or bromine anymore. So we've got our homologous series. You'll recall from year 11, hopefully. Remember your prefixes: meth, eth, prop, but, pent, hex, hept, oct, non and dec. The rest of it you can probably work out. Cycloalkanes, you can join the ends of an alkane, or an alkene for that matter, into a ring. Note when you do so, you lose two hydrogens, as we've got two carbons that are bonded to each other rather than bonded to the hydrogen at the end of the chain. Now, again, like lots of organic structures, they're much easier to see the sense of when you draw them skeletally. Each vertex is a carbon, and you can work out how many hydrogens by how many bonds each carbon needs. Remember benzene, an aromatic compound in which each carbon has got one hydrogen attached to it, is connected to two other carbons, therefore has one unpaired electron. Those 6 unpaired electrons are shared round the ring. They could theoretically have two alternate double bond structures. However, they're actually intermediate between them. Each of the bond is like a 1.5 bond. The 6 electrons are said to be delocalized, and we certainly draw it like that. So recognise what that structure means. It's 6 carbons in a ring, each carbon has got a hydrogen attached, and each bond is intermediate between a single and a double bond. Okay, let's do naming. Why do we bother? Because getting exact molecular structures correct is worth a lot of money to drug companies. One reason. If you need to be able to describe what you're doing, you need to be able to name your compounds. So that particular lovely thing is Lipitor, and it's an extremely profitable molecule. So let's start with something a little bit simpler. And like I say, hopefully this is revision from year 11. So what do? Find the longest continuous chain of carbon atoms, and what have we got? Straight down the middle, in this case, it is a pent molecule. Then identify all of the extra bits that we've got to name, all the side chains functional groups. And that means we've got in this case, we've got a double bond and we've got a methyl group. And which end are we going to number the carbons from? The end closest to the major functional group, in this case the double bond. So carbon number 1, 2, 3, 4, 5, which makes it 3-methyl pent-1-ene. So the major functional group, the most important functional group, goes in the end as a suffix. In this case, it's basically just the double bond which does that. And the methyl group attached as a prefix. Everything else gets attached as a prefix. This one, we've got, again, let's go straight down the middle for our main chain. 6 carbons makes it a hex. This time we've got lots of things to identify. We're going to number the carbons from the end closest to the double bond. Well, in this case, there's double bonds right on each end. So instead, we'll go for the end closest to a side chain as well. So we'll number them from the left. Now, the double bonds as a suffix, well, we've got 2 of them. So it's going to be hexadiene, starting at carbon number 1 and 5. So hexa-1,5-diene. Remember your prefixes for multiple groups. Di, tri, tetra, etc. Note that we put a little A in there just so that English doesn't like too many consonants running together. And then the methyl groups as prefixes. How many methyl groups do we have? 3. So it will be trimethyl. Each methyl group needs its own number. So 2, 3, 3. Trimethyl hexa-1,5-diene. Okay, now this one, the main chain goes round the corner. Remember, all our nice right angles here are totally artificial, everything's tetrahedral. So we go around the corner, how many carbons do we get? We get 3, 7, so that will be a hect. Then our side chains become that methyl group and that ethyl group. This is the end closest to the side chain, of course. Now that's an ethyl group because it's 2 carbons together that are attached to the main chain just by 1 bond. So it's going to be, we've got a methyl group attached to carbon number 3, we've got an ethyl group attached to carbon number 4, and of course our prefixes have to be alphabetical. So 4-ethyl, 3-methyl heptane. Okay, what have we got? Well, we're going around the corner again. So we have another hept molecule. Heptene. We're going to number the carbons from the left, from the right, like so. Going to name the side chain. It's a methyl, so 5-methyl. Hept-2-ene. Now, so it's 5-methyl hept-2-ene, but is it cis or trans? You can see by the way it's drawn out here, we've got the hydrogens are going in opposite directions, so the major functional groups must also be going in opposite directions. Therefore it is trans or E. You can go back the other way and you can draw the structures. That's nice and easy. Hex means you draw 6 carbons down the middle. Then number them from left to right. Probably don't even need to write them in. Chuck the double bond starting at carbon number 2. The methyl groups at 3 and 4. Then chuck in the hydrogens as you need. Okay, do the questions, submit them online, and I'll give you the answers.